Can you hear me? Yeah. Okay. Yeah, thank you for the introduction, and I'd like to thank the organizers for giving me the opportunity, and I also thank you all for showing up. So I'm going to talk about from semantic to relational VOAs, which is based on my work with Dongmin Kim and Hongjae Lee, who is one of the organizers of this workshop, and also some work in progress with Hee-Jun Son and Baek-Yeon Park. They are the PhD students, and they are in the audience. So let me begin my talk with some curious observation made by two great mathematicians in about 25 years ago. What they found is that they consider some certain non-hyperbolic string manifold, which is usually denoted by the sigma 235, which is sometimes called the Poincare homologous spheres, and which can be given by this tensor representation. And what they did is that they computed some quantum invariant, which is called the tubularity invariant, which is just nothing but the pattern function on the Chern-Simons series, Chern-Simons series on this manifold, and do some mysterious operation, which I cannot understand, and they found some Q series, and they claim that this Q series becomes some modular form, have very nice property of modularity, which is become the modular form of degree 3/2. This is very curious and visionary observation, I think. And this modular form actually is very closely related to the vacuum character of the rational VOA, which is one of the main topic of my talk. So rational VOA is there are very rigorous mathematical differential for rational VOA, but I skipped that, and this is just nothing but some symmetry of chiral rational confined field series. So in my talk, also I will use this notation, which is called the tensor representation. So I believe you are not so familiar with this tensor representation. Let me begin with some basic mathematics on the three manifold. So to construct the three manifold, we use the knot and the link inside the three sphere, which can be regarded as a one-point compactification of R3. So this knot is called the PK knot, and sometimes denoted by PO1. PO just simply means that there is a PO crossing, and one is just the first knot with 4 crossings. And this is called the 5-2 knot. And here we will also consider some one PQ torus knot, which is divided by 2 coprime non-negative integers, and these are the torus knots. And then we are considering some knot or link complement on 3 spheres, which is given by some denoted by this one, S3, K, color K denoted a knot or link. This is obtained by the 3 sphere where we are removing some tubular neighborhood of this knot. So we are considering the PK knot complement, and we are considering the PK knot and make it big, and we remove it from the 3 sphere, and we will get a 3 manifold with torus boundary. That manifold will be denoted by this knot complement. And then filling operation is that we are gluing back the solid torus to this knot complement. Knot complement has two torus, and the solid torus has 2 torus. And there is some ways of gluing this solid torus to back to this knot complement, which is denoted by the slope P and Q, which are the coprime numbers, and this can be regarded as rational numbers. And the gluing rule is simply given by this one. So in this knot complement, and their boundary is 2 torus, and there are 2 bases of one cycle, and this is called the meridian and longitude. And we are gluing some linear combination of this meridian longitude to some shrinkable cycle of this solid torus. This is a definition of dense surgery. So there is very mathematical theorem saying that all the 3 manifolds can be constructed basically in this way. So if we are considering the PK knot with the PQ surgery, I will usually use just draw the knot, and we assign some fractional number, and we will define this 3 manifold. This is my notation. So now you can imagine that this manifold, we're starting from the 4 component of a link. And for each component, we are doing damping with the slope 0 and -2 and 3 and 5, and this will give this homological Poincare sphere. And at the end of some mysterious operation, which I cannot understand fully, and they found that some quantum invariant of this one gives this very nice modular property. But I don't know why, but they miss that if you divide by this modular form with some dedicated eta function, which has a degree half, then this becomes the modular form. And this actually becomes the character of the some Best-Junior Victor model, G2 Chonsal level 1. So this is the character of the rational VOA up to this dedicated eta function. So I'm very curious why they missed at this point. So what they found is that given three manifold with a quantum invariant called the duality invariant, and they found doing some mathematically some operation, then they found some rational VOA characters. This, yeah. Oh, I don't need to. This is a hyperbolic knot, and these are non-hyperbolic. Yeah.
What is this?
G2 is a G2 group exceptional group G2. G2 Chonsal level 1 Best-Junior model. So yeah. So, and there's a lot of follow-up, and the one interesting is that we do the similar procedure for this torus knot complement, which is I denote this torus knot labeled by PAQ. And interestingly, this procedure will give the vacuum character of the Virasoro-Amelia model. So yeah, so it's very surprising and yeah, result. So very exactly the same labeling. So Virasoro-Amelia models, we know that these are labeled by two co-prime numbers, and this torus knot or co-prime numbers, and they are exactly same. So my goal is that this observation makes sense that there is some correspondence between some three manifold and some rational VOA. So the natural question is which three manifold will give a rational VOA under this procedure, mysterious procedure, and why, how this correspondence work. This is the main goal of my talk. So this is the outline of my talk. So I will explain that this curious observation by mathematician almost 25 years ago, and we give a physical explanation using this correspondence, using the bunch of correspondence recently found. So first, there is a very famous work, so-called the 3D correspondence, which relate the three manifold to 3D n equal to k series. This is the first step. And then from the 3D, and for certain class of nice 3D n equal to k series, we can assign some topological field theory and also assign some rational VOA at the boundary. This is a very recent development, and I believe that Songjun gave us some brief review on this subject. And this is then combining these two correspondence, and we can expect that for certain 3 manifold, then we get some 3D n to k theory, which will have a chance to give the 3D TKP or rational VOA on the boundary. So this is we expect that this is the reason why we found this relation. So each correspondence are well studied very recently. This correspondence is already more than is almost 15 years old, and this is very quite recently, but this all corresponds very well studied. So combining this one, then one can check that this torus knot complement cases as expected. Then this corresponds, we get a Virasoro-Amelia model. And further, we can extend that to some one-function torus bundle cases. In these cases, we find some new class of the rational VOA, which may imply that there exists some new class of the rational Poisson field theory, which I will call the Hagelov RCFT, generalized non-Hagelov RCFT, which is listed in the literature. So this is a outline of my talk. So let me start. So I will review this part and combine this part. And so let me briefly review the 3D correspondence, which assign some 3 manifold, which is denoted by in this notation, to 3D n equal to k theory, which will be denoted by Tm. And this motivation comes from the M5 brains. M5, as you know, and M theory there is some very mysterious object called M5 brains, which is a six-dimensional object. And the world volume theory is, we know that world volume theory is described by some non-trivial compound field theory, which we usually denote the 60,0 theories. And we are, in my talk, we mostly focus on the number of M5 brains too, then this corresponds to A1,0 theory. And then we can compactify some internal three manifolds with some partial topology twisting along this three manifold. Then when the compactification, we will get the 3D n equal to k theory, which are labeled by this internal three manifold. From this map, we can naturally assign a 3D manifold to 3D k theories. So in my talks, but there are lots of subtlety in the compactification, and there could be several branches, and I will focus on some irreducible component of this compactification. And this our theory is better to call it T irreducible because it only my theory in my talk will see some irreducible component of this compactification, which actually this is a T irreducible, but for simplicity I will erase this subscript. So anyway, so there is some 3D n equal to k theory. For given any three manifold, we can assign a 3D n equal to k theory from this procedure. And not only we expect that there is a 3D k theory labeled by three manifold, and people also know how to express construct k theory description of this three manifold from some internal data of the topological data of a three manifold. So this map is very concrete. So if you give a three manifold and you do some topological data, you can easily cook up the 3D n equal to k theories. So I will briefly that procedure. For that procedure, we also need to introduce some more mathematics, which is ideal triangulation, which is firstly introduced by Thurston to construct the hyperstructure of this knot component, something like that. And his idea is something like that. We are considering the knot complement, figure knot complement. Then it is very difficult to imagine that he showed that this can be glued by these two ideal tetrahedron and the ideal tetrahedron. So if you glue it in this way, then you can get this figure knot complement. Yeah, this is very difficult to imagine, but anyway, so this seems to be true. And his original motivation was that for each ideal tetrahedron, we assign hyperbolic structure, and we can assign a hyperbolic structure, and they glue smoothly, then we can assign this knot complement hyperbolic structure. In this way, he proved that this figure knot complement have hyperbolic structures. So anyway, this is a very well-known mathematical fact. And another mathematics is that for this in the ideal triangulation, people Dongmin and Jagier found that ideal triangulation have very nice symplectic structures. And basically, so if given ideal triangulation, we can assign some symplectic matrices, integer value symplectic matrix, whose size is given by the 2R. R is the number of tetrahedron in the ideal triangulation. And this matrix can be block diagonalized by the A, B, C, D matrices. Each are the R times R matrix, and this A, B, C, D matrix are so-called Dongmin matrices. So this Dongmin matrix can be obtained by some gluing topological combinatorial data of gluing equations. So I'm not going into details, but this for given ideal triangulation, there is some systematic way to obtain these gluing matrices. And one subtlety is that this matrix depends on not only the topology of a three manifold, but it also depends on the choice of the ideal triangulation, and also choice of some secret choice of the assigning of some x parameter, and some other choices. So this is not unique, but up to some choices, this can be uniquely determined. And then using this data, we will construct the corresponding 3D series. And these are the all data we need to use. So three manifold, ideal triangulation, and there we can assign some Simpleton matrix, and then we have some ABCD matrices. Then you can construct the field series. So let me give a brief introduction to 3D n equals 2 gauge series. Generally, 3D n equals 2 gauge series are determined by the choice of the gauge group and the method content and the consignment level and the superpotential. For our purpose, we will consider the following class. This is denoted by the consignment level K matrix and the superpotential deformation. We are considering just the U1 to the R. Gauge group is already to the U1 to the R. And coupled to R chiral multiplet. And this method charges are weighted the identity matrix. It means that first chiral charged on only the first gauge group, and the second one is charged on second gauge group with the consignment level K. And with some, we are doing some superpotential deformation using some half-base chiral primary operators. So these are the defining UV data of this gauge series. Choice of the K matrix, which is symmetric integer valued matrices, and the choice of the this superpotential. And in this theory, there's no this because charge assignment is just the identity matrices. All the charges are positive. There's no way to construct the gauge invariant operator using just the chiral multiplet. But in this series, in 3D, there is a so-called monopole operators. There could be some monopole operator, gauge invariant monopole operator, which are denoted by the M and E. M denoted the monopole flux, M flux, which take the values in Z to the R. And the E is some electric charge dressed by some chiral multiplet. And upon a proper choice of M and E, then this operator can become some gauge invariant, and also can be a half-base operator, and they can enter into the superpotentials. More rigorously, so to be this data should be subject to this kind of some very some concrete mathematical relation to guarantee that this is gauge invariant operator and this become half-base chiral primary operators. And on the top of that, this superpotential should be relevant in order to make this superpotential deformation non-trivial. So we can further require that this operator should be relevant, and there's only finite many choices of ME for each given K. So in the sense that this theory is almost determined by the K up to some finite choices of superpotential. So this K, yeah, it determined this this series. Then their construction is that some 3 manifolds, we can find this ABCD matrices, ideal triangulation for quick and cases, this one. And their claim is that the corresponding 3D theory, labeled by 3D theory, is given by the 3D n equal to gauge theory, whose consignment level K is given by the B2 inverse A. This is their claim. And they check that this TM is not actually dependent on the topology of 3 manifold. It does not depend on the ideal triangulation and some choice of some cyclic choice of the parameter, H parameters, and they are all related by the IR dualities. So this TM, IR physics of this TM only depend on the choice of the internal manifold and not other choices. So this is, I think, a very beautiful construction. So this is their construction. And they give a lot of non-trivial consist check. So anyway, so the main message of this slide is that for given 3 manifold, there is very express construction field theory. You can, using some fancy mathematics, using the ideal triangulation. And anyway, so we have a very concrete field theory description. And further, we can also do the so far, we have constructed this knot complement or something like this one, which have a torus boundary. And we can also do some closed manifold by incorporating dentailing in the 3D correspondence. And dentailing operation is just some gauging some SO3 flavor symmetry. And this construction is also very beautiful in the sense that this resulting 3D theory only depends on also 3 manifold itself. So for given 3 manifold, the tensor representation is not unique. There are infinite many ways of describing using the tensor representation, and to this assignment to make sense, each assignment give the same theory, and this work. So this is in this way we can construct some 3D theory labeled by 3D manifold, which only depend on IR physics, which only depend on the internal 3D manifold and then no other data. So yeah, so anyway, there is very concrete field theory description. Yeah, so yeah, then yeah, I will explain how recent development how from the N-2 case theory to construct the 3D TKFT and some rational VOA. So do you have any questions so far?
You mean that you always find the Lagrangian base description for arbitrary?
Yeah. If you choose one tensor description and you choose some ideal triangulation of this not or link, then you can assign some additional choices, and then you get some field theory description, and the final field theory IR physics only depend on this 3D manifold itself. It doesn't depend on which IR triangulation you're using and which tensor representation you are using. Yeah, that's the result. So now I'm going to talk about how to construct some rational VOA from the 3D n equals to k series. So usually we have some 3D n equals to k theory, which are generally determined by gauge group and Chanson level and scope potential. We are considering some IR phase of this k series, and there are two possible cases when this has no mass gap or this has a unit when have a mass gap cases. Mass gap, if this theory has a mass gap, we know that this theory will flow to the three-dimensional unitary topological field theories. Yeah, this is in a sense can be regarded as the definition of the three-dimensional topological field theory in physics. And so if there is a mass gap, it can be trivially gapped theory. It means that it can be a trivially topological field theory, but anyway, so if this theory has a mass gap, then it will flow to the topological field theory. This is one way to obtain the topological field theory from the unitary topological. This is always unitary TKFT because we are starting from the unitary series. And the unit, this universal group is also preserving the unitarity, so we get some unitary TKFT. And if there is no mass gap, we expect that this will flow to generically to the 3D n equal to Spock field series. But in these cases, there's also, we have several possibilities. Maybe it just flows to the just genuine n equal 2 and 3 CFT, but some cases, some very strange thing happens. This theory in the UV description only have n equal 2 theory, but has some enhanced supersymmetry in the IR, and can have the n equal 4 Spock field series, can flow to the with some supersymmetry enhancement cases. And in the 2D enhancement cases, there's also we can define some two cases, divided into two cases. First one is that this n equals 4 CFT corresponds to some rank 0 cases, which I will explain what's mean by the rank 0, and the non-rank 0 cases. And the one nice thing about this rank 0 case is that after doing a topology twisting, we will get some non-unitary TKFTs. So one may consider some topology twisting for non-rank 0 cases, but the resulting TKFTs are not in a sense that usual sense of TKFT is extended TKFT. But the rank 0 cases, after topology twisting, we will get some non-unitary conventional TKFT, which are described by the semi-simple finite modular tensor category. So this is one nice thing of this one. So this is the way to construct TKFTs. One is unitary cases and non-unitary cases from this 3D n equal 2 k series. So let me explain what's the meaning of the being rank 0. So rank 0 is CFTs are the recently found exotic and the simplest class of 3D n equal 4 CFT. Rank 0 means that there's no Higgs and Coulomb branches. So, and this is very special in 3D because that people believe that in higher dimension, there is no such example with the A-spot chart. So let me give a very simple example of this rank 0 CFT, which I will call this the minimal rank 0 CFT. So this minimal rank 0 CFT, I will denote by T minimum series. This does not allow the UV description with the manifest and proposed symmetry. So this theory allows some UV description with the manifest 3D n equal 2 gauge theory, and which is just given by some U1 consignment theory coupled to the single chiral with the transition level 2 without any spoke potential. It's very simple theory. And in this paper, we argue that this theory experiences supersymmetry enhancement, and this will flow to the 3D n equal to CFT, and this CFT doesn't have any Coulomb Higgs branches. So this becomes the 3D n equal to rank 0 CFT, which I will call the T minimum theory. And in this symmetry enhancement, in this theory, this is U1 gauge theory coupled to one chiral. So there is some U1 topological symmetry associated with the magnetic charge. And there's also UV manifest n equal to supersymmetry, and which has U1 R symmetry. And along the RG, they are combined, and the two become a SO4 R symmetry and become a R symmetry of the N4 CFTs. And we have lots of the non-trivial evidence for the SUGI enhancement. And yeah, so this theory has very non-trivial supersymmetry enhancement and flow to the rank 0 CFT. And the nice thing about this rank 0 CFT is that after topology twisting, after A-B topology twisting, and this will give a non-unitary TKFTs. In the sense that the TKFT, which are described by very least mathematical structure called the modular tensor category, finite semi-simple tensor category. One may consider some topology twisting for general and for CFT, but if it's not the rank 0 theory, then the resulting TKFT is not described by this modular tensor category, but some extended TKFT structures. And like some unitary cases, we know that for unitary cases, if this is we choose the Chern-Simon theory, and this has some boundary mode, which describes some rational VOA, which is best similar return model. And the non-unitary cases also, we can consider some topology twist Volcker theory, and we can consider boundary degree of freedom and certain nice boundary condition. Then this will support some non-unitary rational VOA. It's in a very similar split as for unitary cases, which is very well known. And recently we found that in this using the rank 0 theory, we can also construct this kind of the Volcker theory is a non-unitary TKFT, and the boundary theories for some non-unitary rational VOA. So we can obtain this starting from the very clever choice of the gauge group and the Chern-Simon level and spoke potential. Some cases, generically we will get some this n equal to CFT, but some nice cases we will have some non-trivial dynamically generated mass gap and can have a unitary TKFT. And some cases, some non-trivial supersymmetry enhancement happen, and we can have some rank 0 cases. In that cases, we can construct a non-unitary TKFT. This is a way to construct a non-unitary TKFT. And also at the boundary of this Volcker theory, we can also support a non-unitary rational VOA. For these cases, unitary rational VOA, and these cases, we can support the non-unitary rational VOA. Yeah, and the truths are, so in general, it's very difficult to analyze the IR page of the gauge theory, but we have enough supersymmetry which can be used for supersymmetry localization, and then which compute the RG invariant frequency pattern function. So using this development, we can determine these IR pages using these localizations. For example, if this theory, n equal to gauge theory flow to has a mass gap and flow to unitary TKFT, and then its Spokova index should be always 1. And if the Spokova index becomes 1, then this is a strong signal that this theory developed to a mass gap and flow to the unitary TKFT. So this is a summary. So if you choose a clever choice of the UV data, then in some cases, the Volcker theory flow to some unitary TKFT or rank 0 and CFT, and this will give a unitary TKFT and a non-unitary TKFT. and the boundary, and we can support the rational VOA. So from this construction, we can construct the rational VOA from the three-dimensional n equal to gauge series. And we can also compute the very concrete quantity of this rational VOA, which is called the vacuum characters, by computing so-called Hopf index, which is basically some partition function on D2 times S1 with a nice boundary condition along this boundary. And we can also, construct all the non-vacuum characters by inserting some loop operator inside this solid torus, and we can also compute the full characters of this boundary relational VOAs. So let me give a very concrete example. As I mentioned, that the simplest example is T minimum model, which is just given by the Chern level 2, which is 1-by-1 matrix. It means that the gauge group is U1 coupled to the 1 chiral of charge 1, and Chern level is 2. And in the RG, this theory experience non-trivial supersymmetric enhancement, and this will flow the minimal rank 0 safety, which is I call T minimum. And after twisting, A twisting, and it turns out that this theory becomes some Liang TQFT, and the bulk boundary correspond, and this theory support at the boundary some Liang VOA. And we can expressly construct these characters by computing this Hopf index using the UV description, and we will get some vacuum character over Liang RCFT from this UV description. And we can extend this exercise more complicated examples, such as that we consider this K matrices. It means that we are considering the U1 to the cubic gauge theory coupled to 3 chiral, and with this Chern level, and with some superpotential labeled by this M and Lee. And we argue that this theory flow to the rank 0 safety in the IR, and we can also compute the Hopf index of this one, and we found that this character becomes some new expression for this vacuum character of the W3 minimum index. Yeah, so now we can combine the two correspondence, and so starting from the 3D manifold, I can assign a 3D n equal to gauge theory, and from 3D n equal to gauge theory, and using the RG learning and some temporal twisting, and going to boundary, and we can also relate the next VOA. So we will combine these two correspondence. So for that, we need to understand the IR page of this TM series. So I forgot to mention the references, and but some work with Hitcher several years ago. So we found that when this 3 manifold is a closed hyperwall manifold, and this theory always flows to the non-trivial n equal to 4 shaft generically. But if we choose the 3 manifold of certain type, this kind of the Zipfort fiber manifold with 3 fibers, then this always flow to some cases this flow to the unitary TQFT, and some cases this flow to the rank 0 CFT. So in these cases, we can assign a rational VOA at the boundary of this TM series. So as a concrete example, so we studied this series, and we found that this is correct. And for the Poincare homological sphere cases, this corresponds to TQ choice given by this one, and according to this criterion, and this will flow to the theoretic gauge theory will flow to the unitary TQFT, and actually it turns out that this unitary TQFT is given by the T2 Chern level 1 Chern series. So this will give, and this theory is unitary Chern theory, and there is a boundary Besmino-Witter model, and this boundary theory will support G2 Chern level 1 Besmino-Witter rational VOA. So this will give some physical understanding why they found that starting from this homological point cloud homological sphere, they get some characters of the G2 천삼 level 1 base unique model. Yeah. And we can also further and the linear models and the mathematics also found that from the torus knot given by the PQ torus knot, they can construct a assign a linear model. Okay, they can reproduce Virasoro linear model characters from some complicated computation. And in our picture, so we are considering some 3D theory which is labeled by some knot complement of torus knot complement. This PQ denote the PQ torus knot. And using the field theoretical construction based on this ideal triangulation of this knot complement, and doing the localization, we can analyze this IR phase. And from case by case study, we found that this theory, gauge theory, always have a mass gap in when this difference between P and Q is 1. And we found that this theory always have a non-trivial supersymmetric enhancement and flow to length zero safety when this is cases. And for this cases, so using this one, we can define some TQFT labeled by and the P and Q, which is defined as just the IR TQFT for unitary cases, and the length zero cases, this is topology twisted theory for the IR CFT. Then this modular tensor category structure of this TQFTs are exactly the same as the modular tensor category of this rational VOA, Virasoro linear model VOAs. So if there is a rational CFT, there is some topological structure called the modular tensor category, and they vertical theory also has the same modular tensor category structures. And this can be checked at the level of the modular data, not the full modular MTC data, but we confirm that at the level of modular data, and they agree. And recall that this Virasoro linear model is unitary when this difference is 1, and this is non-unitary when this is difference is bigger than 1. This is also compatible with this picture. Because in this case, this is a unitary TQFT, and this cases, the resulting topological field theory is non-unitary due to the topological twisting. Yeah, I think I'm too fast, so do you have any questions so far? Yeah, so let me give a concrete example. So it's a 5-2 knot. And this 5-2 knot is given by this knot. And then we should consider some ideal triangulation of this knot complement. Yeah, of course, it's very difficult to imagine that the ideal triangulation of this knot complement. But fortunately, there is a very nice mathematical some computer software called Snappy, developed by the knot theorist. And this theory, if we input that this manifold, which is in the Snappy notation, this manifold is called the 5 knot, and ask the gluing equation for this knot complement, and they give this answer, and this will determine this Neumann-Jagier matrices. Once we have this matrices, with some simple linear algebra calculation, we can get this Neumann-Jagier matrices can be read off in this way. And then this in Neumann-Jagier matrix, so we can determine the K matrices, which is B2 inverse A. And then the corresponding theory will correspond to this K series. And this is nothing but you want to the cubic theory coupled to the 3 chirals with the Chern-Simons levels given by these matrices. And then we can analyze this IR page of this series using the supersymmetric localization. And this is already done by this paper. And they found that this theory is actually IR dual to the T minimum theories, which is for the Virasoro linear model M25 Liang model at the boundary. So this is compatible. And using this UV gauge theory description, we can also compute the half index, D2 times S1 partial function, and this will give the vacuum character of the Virasoro linear model. So we can do this kinds of the tedious computation for every PQ, and we found that this always work. Yeah, and another interesting application of our construction is that using this construction, we can construct some new class of the rational VOAs. This comes from the three manifolds called the once function corresponder. So this manifold is labeled by some SL2G element. So this is manifold is constructed by in this way. We are considering some Riemann surface times once function torus times a sub interval. And we are gluing the two interval by some SL2G twist. And this is the definition of this one function corresponder. And this manifold are labeled by some conjugate class of the choice of this monodromy pi matrices. So when this pi is identity, this is starting about the once function torus times occur. And interestingly, this theory always flow to the rank 0 CFT in the IR. Theory, once function corresponder. And the more interesting is that the resulting TQFTs has very exact modular data, which is not known in the literature. So it seems that this TQFT obtained by topological twisting the theory of this rank 0 CFT seems to give us some new class of the rational, the non-unitary TQFT as well as non-unitary rational CFTs. So here is some expressed form of this modular data for when the monodromy is given by STK, and this is some concrete expression, modular data SI matrices. And this matrix is, this element is very exact in the sense that this element cannot be written as some simple product of a sign function. If this TQFT can be constructed by some Bessemer-Witten model of some gauge group, classical gauge group, then the issue can be written as some simple product of the sign function, but this cannot be done in this way. So this is a signal that this is actually the very exact class of the non-unitary TQFT. And when K equals 11 cases, this modular data is turns out to be some Galois conjugate of the so-called Hagelhoff TQFTs, which is the famous for being the exotic class of the candidate for the exotic TQFTs. So in this region, so I will call this TQFT as a generalized non-unitary Hagelhoff TQFTs. And this boundary, we are considering the boundary, and we expect that upon a suitable boundary condition, it will support generalized non-unitary Hagelhoff VOA. So we can do further, and we can actually, using this field theory description, this is a once function corresponder, also can be ideally triangulated, and then using the ideal triangulation, and then we can obtain this Neumann-Jaeger matrices, and using Neumann-Jaeger matrix, we can construct the field theory description. And this UV field theory description, and applying some localization formula, we can get a half index. And it turns out that this half index become a nice character of rational VOA. So this become this Chi0 can be converted into the full consist characters with compatibility with the modular data. Maybe this will give the strong evidence that there really exists some generalized non-unitary Hagelhoff rational VOA. Yeah.
The first denominator two compared to the step 2.
Yeah.
It's not typo.
Yeah, it's not typo, and I did a little cheating. So usually in this K matrix, it's not integer valued. There could be some half, and the correct way to understand this half is that the charge is somehow better charge is 2, and the Chern-Simons level is some doubled, something like that. So there is why we have 2.
That means something you have Z2 1.
Yeah. Z2 one-form symmetry, and this Z2 one-form symmetry is correspond to this one-form symmetry of decoupled TQFT. Yeah.
Sorry. So if you have K equals
1 or 2, the central charge is positive, but you still get an yeah, so I also did some, yeah, this is condition is satisfied. And the K equal 1 and 2, this is not satisfied. Yeah. So, yeah. In this field shear analysis of this one, T equal 1 or 2 cases, it flows to unitary decrypted. Yeah, unitary decrypted with some decoupled chirals. Yeah.
Okay, can I ask what's the violation condition? Is it the checksum coupling with the complex?
No, this is a constraint for the 3 manifold, and so once the function transponder is hyperbolic, it's non-hyperbolic. When this is satisfied, it is known that this once the function transponder is hyperbolic, and this is not satisfied, it is known that this once the function transponder is non-hyperbolic. Yeah.
And which side of the function?
This is yeah. So the manifold is yeah. I use that. So the manifold is given by so we are considering one torus with the functors, and there is some interval, and then we are doing some twisting and such. Yeah, this is the manifold. Yeah, and the resulting manifold has only one torus boundary, which also is this function. Yeah.
You get to be one more.
Huh? It's hyperbolic when the trace pi 2. Yeah. So if it's pi is identity, that of course it is not hyperbolic. It's yeah.
You get one more function, and then what happened? That was my question.
If you have, we are considering this one.
Yeah.
I don't know. Yeah, I don't know. I don't know how to. Yeah.
Yes, we have the two Johnson. One of the.
Yeah. That I haven't. Yeah. Talked about that. Yeah. So yeah. So let me summarize. So from this map from 3 manifold to 3D anechoic gauge theory, and from the map from the 3D anechoic gauge, 3D TFT and the rational VOA, and we can find that some concrete map from the certain nice choice of 3 manifold will result in give a 3-dimensional, 2-dimensional 3D TFT and the rational VOA at the boundary. So concrete example was that when this is a torus knot cases, and this will give a Virasoro linear model, and this once torus cases, it will give a generalized Hagelov RCFT. Or maybe this will give us some prediction of the existence of new RCFTs. And though this all construction can be generalized in the obvious cell, first we can replace by 2 m pi brane to n m pi branes. And we are considering some torus knot, and the n equal 2 cases, it was a Virasoro linear model, and the general n cases, we expect it will give a corresponding WM linear model, labeled by same way. And this also generalized Hagelov can be also further generalized, and so will be generalized Hagelov RCFT, and maybe in this way, there are lots of the labeling of geometric labeling for this kind of Hagelov RCFT, and this may give a full general Hagelov type of RCFTs. And further also, I believe that we can replace the torus knot cases. We can arbitrarily non-hyperbolic knot or even link. And this corresponding theory, 3D theory, always have a mass gap or have a suitiness to any for length 0 CFT, and we can assign a rational VOA. So maybe, yeah. So maybe we hope that this sum of this non-hyperbolic manifold and non-hyperbolic knot and link will give us some new RCFT or some just reverse the known RCFTs. Yeah. So thank you for the question.
Questions?
So in your procedure of going from 3 manifold to VOA, there's a step of choosing the boundary conditions. I think you, right? And then it's a different boundary conditions. You can get different VOAs. They share the same modular tensor category.
Yeah.
Now, on the other hand, you can also consider 4 manifolds where to 4 manifolds, you get VOA, associate VOA in a unique way, right? When you wrap M5 brains on four manifolds.
4 manifold, then we will get a 2D theory.
Yeah, 2D 0,2 theory.
0.2 theory. Yeah,
Right. Now when you what?
Yeah, so it is not rational.
So now when you have a 4 manifold with a boundary, the 3 manifold, then it's gonna give you 0,2 boundary condition in your 3D theory. So I was wondering, for example, if you have M3, you can consider 4 manifolds that bound your M3, give you various boundary conditions. So I wonder if if you can sort of back engineer the 4 manifolds that.
I see. So that's a question. So in this procedure, what we did is that, as I mentioned, that this theory, so ideal triangulation, there's no unique UV description. There are, depending on the choice of ideal triangulation and the choice of the some assignment of the H parameters, we will get a lot of the dual frame. And what we are doing is that we fix the one boundary condition and changing the duality. And then see that this half index makes sense. Then we work out in this duality frame. This is what we did. So for example, if you are considering the natural boundary condition of this TK theory is that the Dirichlet boundary condition. But this Dirichlet boundary condition is not well defined when the K matrix is that positive definite. If you write down the half index, it diverges. So what we are doing is that we choose some nice duality frame where the tensile level, under the duality transformation, tensile level K matrix changes, and we can always find one duality frame which K matrix become positive definite. And then we work out that half index in that frame, then it always give consistent rational characters. That's how we treat this boundary condition in this construction. I'm not sure how this is related to your question to this 4 manifold extension and try to find some natural boundary condition from the 4 manifold side, but I don't know how to.
Okay. Let me ask you one question. So you talked about when alpha is 0, it corresponds to the vacuum character, but you didn't explain when alpha is generic cases. So what kind of operator are you inserting at the origin for the half index?
Yeah, in this cases, so in these papers we couldn't do it because that we cannot find that which Wilson loop which loop operator we should insert to get some non-vacuum characters. But what we did is that we have this vacuum characters, and we know the full S matrix is. Then there is a very nice way to construct the full characters developed by mathematician, and then we check that this will give us full conscious characters. But later, so one of my PhD students found that there is we can insert some loop operator, but not the one simple gauge group, but some linear combination of the Wilson loop, then we will reproduce the full characters. Yeah, so in that sense, we know that which loop operator will correspond to this simple object, but this in the UV description, this simple loop operator is not given by the simple gauge Wilson loop, but some combination of the simple Wilson loop.
So there is at this moment no systematic way to construct the alpha representation.
Yeah, trial and error. So there are some lots of conscious check we can do. So if some UV operator becomes some simple object, and it should satisfy non-trivial condition. And if we can check that whether it becomes the simple object or not, there is some very concrete criterion using the Spock index. And once we have a candidate, then we can check it is simple or not. But there's no way to find that general way to find that.
But you always give the same boundary condition at the boundary of this disk.
Same boundary condition, and just inserting the additional loop operator will give non-vacuum characters.
Okay, thank you.
Any other questions? If not, let's thank speaker again.